Okay, today my topic is modeling history dependency in network behavior coevolution. Before I go into details, I want to highlight 5 points about today's speech. First, I want to elaborate what kind of research questions do we use a discrete time Markov chain theoretical model. Second, I will give out the mathematical equations this ethical used to develop this model. Third, I will introduce the case the author used to adapt this model. The fourth is that I want to explain some relationship with this model and the time series we have learned. And the last one is to give out some questions for discussion. First, let's look at what problem this model is to solve. That is, in a simple word, to answer how spatial interdependency the network evolve with time. It's interesting to notice that we use spatial lag instead of time lag to reflect the time track on the network change. The basic idea is that current network depends on its previous status. So it's philosophically speaking, they are the same. That means the current format is based on its previous historical track. Before I go into the models, I want to illustrate some basic understanding in network analysis. In a network field, we treat each actor as one node and their relation as link, or in the name of tie. So the actor and the node and tie are the terminology for network analysis. In order to study the path network changes, the author mentions 3 elements should be attended to for the statistic models. First is the exogenous covariance, that is the common exposure of this network to external or internal stimuli. Second is the contagion, that means the interdependency of outcome or behavior across actors. Contagion arises anytime some unit's action affects the marginal utility of others' action. For example, in a network, my behavior depends, or a country's behavior depends on both the policy exposure and its relationship with other countries. The third element should be attended to is the selection effect. That's mainly talking about the homophily and heterophily. Homophily, or never of the difference, is the tendency of the individuals or countries to be clustered in diverse groups, while it's opposite for homophily. So in my understanding, homophily means this group, they share some similar features and they class together. However, for heterophily, the group features may not the same, but they still group together. So complete model should capture 3 of these elements. That is, node effect, and network formation. Therefore, the model is derived from 3 mathematical equations that correspond to the aforementioned 3 effects. First of all, the steady-state path dependency of contagion and selection comprise 2 sets of Markov chains. The first one is temporal autoregressive that observes an actor to maintain behavior at t plus 1 from its status on t. So the first equation describes actor i's probabilities of transition types from period t to t plus 1, regardless of its relation to others. The second equation estimates the actor's propensities towards action 1, making the tie, or 0, not making the tie with the other. So the second equation captures the contagion effect, measuring the probability of individual or actors' preference to be connected or not be connected. It's worth mentioning that all these models all those equations are based on the dyadic relation, that is 1-to-1, only two actors are linked with no direction. When the unit become a dyad, the probability that I and j are collected in period t plus 1 is denoted by the third equation. So the third equation describes that in t plus 1, how likely the two actors can be collected or linked. Of course, the complete model should consider the common exposure factor, that is the exogenous parameter C in this process. I'm sorry I'm not a master of math, but the author, based on these three equations, and they developed this chain model to measure the network change in space. They applied it to some tests, and the figure reveals a result derived from this model. The top left one plotted both behavior and contagion and selection homophilic based on the tie similarity and dissimilarity. So if we apply the three equations to measure the network change, we get the path of the behaviors on the left top figures. And the reason why they have two paths is because they change the value of C. They change the value of the exogenous covariates. If we eliminate homophily effect, we get the top right figures displaying a spatial autoregressive path. So that is only in my understanding, that is only the path reflecting the time. Only the time works on the network. Or it's just a normal time series model. If we skipped observing the two features, the contagion and the selection, then we will get no path dependency graph in the down right corner. And all of these four figures is just to tell us if we want to look at network change with time, we should take account of behavior contagion and homophilic selection to observe their coevolution or path dependency. The function of this model is to forecasting the behavior change for a network. So it suggests that using the logistic discrete time Markov model, that includes the spatial lag model and the independent P model, we can have the prediction or the probability of the network change. Since there is another popular model applied in the network field, that is Sinner's SMOM model, the author also bring this together to make a comparison, and they use the Monte-Carlo evaluation to compare these two models. And the results suggest that if there is low event rate, that means there is fewer shocks. Both strategies works acceptably in favor of the logistic strategy. However, if it at a high event rate, neither strategy managed to gain any appreciable traction on contagion or selection. In the final part of this article, they bring in an article to illustrate how this model is studied. They measured conflict behavior at regime type, the political score, and national compatibility. They used the regime similarity and the power asymmetry to measure the alliance ties. In the result table, you could see that Model 1, Column 1, and 1b are models without covariance, realizing the logistic Markov model equation. Model 2 adds the covariance, and Model 3 applies the Sinner's continuous time Markov model. The significant results shows that heteromorphily, meaning Pacific powers, are more likely to ally or maintain islands with aggressive powers, and conflict behaviors is positively contagious through alliance. All of these support the previous theoretical assumptions. In my final part of the presentation, I propose some questions for discussion and compiled with my own understanding of what I have learned and the relation to this article. First of all, how we could make sure that the network change is one time, one leg, like the AR1, because the Markov chain model, it still assumes that the spatial lag is just one and not two. So do we have some detection or diagnostic test to know what spatial lag is? The second thing is that what models should we use if we treat time as continuous? In this case, we still treat the time as at a discrete variables. That means we do not treat it as continuous, even though the Sinus SMOM model treats it as continuous, but it doesn't work very well. So, in my opinion, if we want to study the network involved with time, is there any other better solutions nowadays to solve this problem? The third question is that what models can we adopt for higher event rate? Because the conclusion from the article suggests that both of these two models work very well when there is lower event rate or fewer shocks. So if I want to know, is there any update advanced models for higher event rate? The last question I want to ask is why couldn't we use ARM or ARIMA to model network dynamic? Since philosophically they are the same, because the network changes even though it's a spatial perspective, but it changes with time. So my question is why we can't use ARM or ARIMA to model network dynamic. And those are the 4 questions I posed for the video discussion. And thanks for your attention. That's all.